Okay, so now that we've talked about Euler's phi function, we can finally talk about these two important theorems in number theory, called Euler's theorem and Fermat's little theorem. And, well, Fermat's little theorem is actually a corollary of Euler's theorem, in the sense that it follows from Euler's theorem. So let me explain why. Euler's theorem says the following. If you have two natural numbers that are coprime, right, GCD of a and m is equal to 1, then if you raise a to the phi function of m, then you get 1 modulo m. Right? It's congruent to 1 modulo m. And, well, what happens if you take m to be a prime number? So if m is a prime, so you have p instead in Fermat's little theorem. If a is a natural number that doesn't have p as a factor, then, well, we know that phi of p for prime numbers is equal to p minus 1. And that just exactly gives you the statement here for Fermat's little theorem. Right? So again, this is what we call a corollary. Right? It's a special case of Euler's theorem. And now you're probably thinking, like, why are we even talking about this, right? What are the applications here? And there are indeed some applications of these theorems that we won't be seeing in our course. But one way that we can use this is, well, to compute remainders. And I'll give you an example. Suppose that you want to compute the remainder when 3 raised to the power of 2020 is divided by 113. Right, so one thing you could do here is to just keep multiplying 3 by itself. Right? Notice a pattern, and you're working modulo 113, right? So you could just keep multiplying. If you get something larger than 113, you just throw copies of that away and make it smaller again. Well, Euler's theorem, and to be precise, Fermat's little theorem, actually help us quite a bit here, in the sense that, well, if we can somehow find a number, right, such that 3 raised to that number is congruent to 1 modulo 113, then that would really help us, right? We could just find maybe a way to decompose 3 to the 2020 into smaller pieces based on this number. Well, okay, so what is 113? Is it coprime with 3? Can we even apply Euler's theorem here? And the answer to this is yes. 113 is actually a prime number, which means it's actually Fermat's little theorem that applies. Right? Again, it's the same thing. You can also say Euler's theorem applies, and it would be a true statement. And so, in fact, the power here is going to be 112, which tells me 3 raised to 112 is just going to give me 1 if I'm working modulo 113. Right? And I didn't have to do anything extra there. That's what the theorem tells me is true. So, how does that help me here? Well, you have 2020 in the power here. So if I can write this as something times 112 plus another thing, right, using your division algorithm, then I know that I only really have to raise 3 to the remainder there, because 3 to the 112 is just going to give me 1 anyway. So, okay, let's divide. All right, 2020 divided by 112, turns out that's 18. And that will give you a remainder of 4. Okay, and what this allows me to do is to write 3 raised to 2020 as 3 raised to 112 times 18 plus 4, right? Just rewriting the exponent there. But now I can write this using my laws of exponents. It's 112 raised to 18 times 3 to the 4th power. All right, and so this is nice. Again, 3 to the 112 by Fermat's little theorem is just 1. That's 1 to the 18. 3 to the 4th power is 81. And so we're actually done. Therefore, 3 raised to 2020 is congruent to 81 modulo 113. Right, which means even if we had this large power of 3, right, we didn't have to divide it by 113 to compute the remainder. We just used Euler's theorem to simplify the calculation in order to recognize that 3 to the 2020 is really the same as 3 to the 4th power modulo 113. And to give you an idea of why Euler's theorem is true, I'm not going to prove it in general here, but I'm going to demonstrate why it's true using 4 and 9 as A and M. All right, so 9 is not a prime number. So again, the statement is this: A raised to phi of M is congruent to 1 modulo M. Again, we need the GCD to be 1. And that's true here as well. 4 is 2 squared, 9 is 3 squared. And so, how do we even see Euler's theorem? How do you even prove it here? How do you compute phi of 9 in the first place? Okay, so phi of 9 is, well, the cardinality of the set of integers from 1 to 9 that are relatively prime with 9. So that's 1, that's 2, not 3, right, because 3 is a factor of 9. 4, 5, not 6, 7, and then 8. So phi of 9 is equal to 6. And so, how does this help me prove it? Well, I want to get eventually to this statement, right? That 4 raised to the 6th power is going to give me 1 modulo 9. And of course, you can just do the multiplication, right, to show it's true, right? But that's not the point of what we're doing here. I'm trying to demonstrate why this comes up here. And look, let's take these 6 integers. 1, 2, 4, 5, 7, and 8, right? And let's multiply all of them by 4 and reduce modulo 9. Okay, so let's multiply by 4. What am I going to get there? 1 becomes 4, 2 becomes 8, 4 becomes 16, which is 7, right? You're reducing modulo 9. 5 becomes 2, 7 becomes 28, which is 1, and then finally 8 becomes 32, which is 5. And you see here that what we just did there was to permute the numbers 1, 2, 4, 5, 7, and 8. Right? In other words, it's a bijection. You multiply everything by 4, and you get the same numbers, just in a different order. And so what this tells me is the product of all these numbers on top and the product of all these numbers at the bottom, they're going to be congruent, right? Because it's all the same numbers. So I can write this as the statement 4 times 1, which is what I got here, times 4 times 2, which is this, times 4 times 4, which gave me that 7 there, 4 times 5, which gave me that 2, 4 times 7, which gave me that 1, and finally 4 times 8, which gave me that 5. So if I multiply everything in the red box together, that should be congruent to, well, just the product of 1, 2, 4, 5, 7, and 8, right? Before I multiplied by 4. So 1, 2, 4, 5, 7, and 8. And this is modulo 9. Aha, and remember one of the properties of congruence we had before. We can cancel numbers from both sides of a congruence as long as it's relatively prime with the modulus. And so the modulus is 9. And well, what do you know? All these numbers are relatively prime with 9. That's why they were in here in the first place when we counted 5, 9. Right? And so cancel the 1. We don't have to, but let's just do it. Cancel the 2. Cancel this 4. Cancel the 5, the 7, and the 8. And look what we have left. 4 to the 6th power. It's now congruent to 1 modulo 9. Which is what Euler's theorem tells us. Right? So in fact, this is how Euler's theorem is proved in general. You just want to show that if you take all the integers such that it's smaller than m and relatively prime with m, then if you take this same set and multiply it by a, then that induces a permutation, and you just get the same numbers. So you take the products of all these numbers in all these sets and set them equivalent to one another in a congruence, and then cancel all these k values from each side. Right? And so that's the idea of the proof there.